at 100. And yeah. And I just, I always feel sad right now because it's when we get to finally we get to these significance tests and we can actually answer interesting questions with all the tools that we've learned, and we don't have much time to do it in. So that's just the way it is, but I'm working on a new course, and that should be ready not this fall, but next fall, so I hope you'll take it. It will be a continuation of this course, and we'll have a notebook, and we'll just continue on and just use a lot of the methods we've developed and base it on the same concepts and have the same sort of very simple approach where we explore interesting everyday questions that have meaning to us using our own data, but we're going to learn more methods, and you'll be able to apply it to more disciplines, to your other courses, and learn more terminology. So that's to come, so it makes me feel a little better. We just did a chi-square test, all right? And remember what the chi-square statistic was. It was the sum, if you remember, the chi-square statistic, let's just write it down again, is the sum of what? Do you remember what it was? It was the observed minus the expected under the null, and what you observe compared to what you'd expect, and it's squared, divided by the expected, that kind of normalizes it, and it's the sum of that, okay? The sum of the observed minus the expected over the expected. Now, and you also have to, it's a series of curves depending on the degrees of freedom. Okay, that's what we did last time, and it was called the chi-square goodness of fit test. Now we have another chi-square statistic. It still uses, you only use this statistic for both chi-square tests. So how does this one differ? Well, this independence test involves two variables. Two variables. Are they independent or are they not? For example, in our survey data, I asked you, maybe not this semester, it's in the homework, are you right-handed, left-handed, or ambidextrous? I don't know if I asked that this semester, but I wondered, does that depend on whether you're male or female? Is there a different distribution for whether you're male or female? So you'd have two variables, handedness and your gender. That's one of the homework problems. And when you have two variables, and the question is whether one depends on the other, and they both have multiple categories, you use a chi-square test. Now, if you just have one variable, like, one variable, like you have this, like let's just say handedness. We're not thinking about males or females. We're just thinking about whether people are right-handed, left-handed, or ambidextrous, okay? And we have a theory. Like I just did this recently because I was just discussing it with somebody who was left-handed. And that person was saying he thought 10% of the population was left-handed. And I said, what percent are ambidextrous? And he thought maybe 5%, and the rest are right-handed. And I said, how would we test that? That would be our model. Our model, we'd have a categories, this would be a goodness of fit test, where our categories, you don't have to write this down, we'd have a box, a goodness of fit, and we'd have a model that we specified, and we'd say, okay, 3 categories. There would be left-handed, there would be right-handed, and there would be ambidextrous. And maybe there really are 10%, 5%, and that would leave 85%. So what would we do? We'd take a sample of people, and ask them what, their handedness, and the null would be, does our observed data fit this model good? We have one sample, one variable. But now let's say we have That's our goodness of fit. You know, we had one sample, and we specify the model. This is the goodness of fit, just to, you know, give you a feel. Okay, goodness of fit. Now what are we going to do? If we're going to have a chi-square independence, and this is what's going to be on your homework, a similar problem, chi-square independence test is not, we don't specify a particular model. We're not interested in that. We're interested in two variables here. We just have one sample. Another way of saying it is one variable, handedness. Okay, and a specified model. Now, if we have a chi-squared independence test, we have two variables. And the one on your homework is handedness. That's one of them. Handedness, is that the right word? Handedness, left, right, or there's three categories. And the other is gender, male or female. Gender, okay? So you could think about it this way. You have two boxes of people. You have males and you have females. And you're not, and you have left-handed, right-handed, and ambidextrous. Left-handed, right, you have three categories. And all you're interested in, you're not specifying what these are, you're just wondering if they're equal or not. Does whether or not you end up, does the percentage distribution of handedness differ among males or females? Does it depend on whether you're male or female, or are those independent? So you have two variables, and it's called each with multiple categories, or you could think of it as two samples with multiple categories. And you do a chi-square independence test, all right? And if you have just two categories in here, then you can code it as ones and zeros. Like if we didn't care about ambidextrous, we could say ones and zeros, and then we could do a two-sample Z. Or this, either one. So that's the idea. Now let's get to it. All right? And I did the same thing here. I explained it with the zodiac example. I said before we had, in our zodiac example, remember we had 12 categories, and we said they were all equally likely. But what if we wanted to compare serial killers to Fortune 400 executives, to the most and least successful people in our society? We wanted to see if their sign distribution was depended on whether their career status depended on sign distribution. So I'm doing the same thing here. Like in the zodiac example that we did, there were 12 categories, and the model was that each was equally likely. All right? Do you remember that? It was that each was equally likely. Now suppose we wanted to compare the distribution of astrological sign among those top executive that those girls in the bathroom wanted to hook. Remember that story? That they were interested in those guys? And they certainly didn't want to hook up with a serial killer. That's far from. So the question could be, is the sign distribution between serial killers and Fortune 400 executives different or not? Does whether you end up one or the other depend on the sign you were born under? Okay, so then you would do a chi-square independence test. And that's basically the idea. Do you want me to spell it out anymore, or do you want me to just get to an example? Example. All right, so I'll spell it out more in the notes if you're interested and want to look at the notes and get them online. I'll spell it out more, but now we'll do a full example. I think that will help you, okay? Sound good? All right, so let's get to an example. Now, so here's an interesting example. This was a study done to see if hepatitis C was related to tattoos or not. Some people were saying, some celebrities were saying that they got hepatitis C. I think it was Pamela Anderson was the first one to say this, that she got hepatitis C from tattoos. And so other celebrities said similar things. So a study was done to see whether this is a possibility. So this is an interesting study. What they did was they investigated the relationship between whether you got tattoos from a parlor, or whether you got it from somewhere else, or whether you had no tattoo at all, and whether you had hepatitis C or not hepatitis C. And it was, these people were convenient because they already had their blood, and they were at a Dallas spinal clinic, and they had lots of photographs of them where they could just count their tattoos and talk to them about their tattoos. And they had no reason to believe that they were at more risk or less risk for hepatitis C than anybody else. So there were 626 of these people, okay? And out of the 626, they found that 47 of them, which is 7.5%, had hepatitis C. And the rest of them, the 92.5%, didn't, okay? And now they thought, all right, let's do a hypothesis test here. The null hypothesis is that the chance of getting hepatitis C is independent of tattoo status. What does that mean? It means it doesn't matter at all. There's no difference between the rates of whether the people who got a tattoo from a parlor, they're going to have a rate, this rate, 7.5% of them will get hep C. The same rate here, whether you got a tattoo for somewhere else, the same rate if you didn't have a tattoo at all. There's no reason to believe that these groups are any different than each other, and the observed differences are just due to the luck of the draw, okay? That's what the null says. And the alternative says, the chance of hepatitis C does depend on your tattoo status. These groups really have different rates of hepatitis C. And if you look at this, 17 out of 52 is nowhere near 7.5%, right? 17 out of 52 is like, what, like 34%. So these differences are way too big to be due to the luck of the draw. So you have to do a test, right? And so that's what we're gonna do. So we're gonna do, remember what our test is, I'm gonna write it up here again. Our test is the chi-square test, and it's equal to the sum of the observed, and you're given the observed. Always given the observed. This is given, always. The given. Observed, given, always. So you always have that. The sum of the observed minus the expected, and this is what you always have to figure out based on your null, that there's no difference. So your expected, you have to figure out based on the null, and then you square it and divide it by your expected. So just like we did with the one sample, goodness of fit, we had to figure out the expecteds, which was pretty easy to do. This is going to be a little bit harder, but not too bad. All right, so we've got this. We just have to figure out the expecteds, plug them in there, and get our statistic. Now, how do we figure out the expected? You always figure out the expected assuming the null is true. If getting hepatitis C has nothing to do with tattoo status, then the proportion of people who have hepatitis C should be the same. 7.5%, 7.5%, 7.5%, because 7.5% of the people total have it. Okay? So, that's what we expect. Now, that would be easy, except chi-square tests always depend on counts. The expected are counts, not proportions. So we have to change the 7.5%, 0.075 is the same as 7.5%. We have to change those to counts. So that makes it a little bit complicated, all right? These are all counts. See, these are not percentages here. So that makes it complicated because we have to do a little bit of math here. And I didn't bring my calculator this time. So let's see what we have to do. So I want 7.5% here, 7.5% here, and 7.5% here, because 7.5, this is 7.5%. 0.075. So I want it across here. So I have to multiply. So I say, okay, of these people, these 52 people, 7.5% of them, 0.075 of the 52, under the null, should have hepatitis C. And this comes out to 3.9. What do you mean, 3.9 of a person? Well, remember, our expected doesn't have to be something that could ever happen. You can't get 3.9 people. You have to either have hepatitis C or you don't. But an expected doesn't have to be something that has to really happen. Like, you know, it's like an average. The average number of people, children is 2.2, that doesn't happen. Okay, so that's what we get there. Now we do the same thing here. 7.5% of 61, and we get 4.6. And we do the same thing here. 7.5%, I'm using 0.075, times what? All these people, most of the people didn't have tattoos. So 7.5% of them, and that is 38.5. Okay? Is everybody clear so far? Questions? Now, what should we do? This better add up to 47, so we better check 3.9 plus 4.6 plus 38.5. Does that add up to 47? It should, if you do it right. Maybe, you know, sometimes you'll have a little rounding error, but it should be about 47. Okay, now let's do the next one. How do we get the next ones? Now, 7.5% have it, so that means 92.5% don't. So that means 92.5 is 0.925 of the 52 should not have hepatitis C. So we have to do that for each one of them. And here we get 48.1, excuse me, that says 40. Let me zoom in a little more so you can see better. Okay, that says 48.1. Okay? And that better add up to 52, and it does. And then we're going to say that 0.925% of the 61 don't have hepatitis C because they're under the null. That's how it would be. And here we get 56.4. Check that it adds up to 61, and it does. So that checks and that checks. And finally, 0.925 of the 513. You multiply those two together, and you get, oh, a lot of people here, because 513 is a big number, 474.5. Add them together, and you do get 513. It checks. All right. And if you added them this way, that's 47 and 48.1 plus 56.4 plus 47. There's a lot of ways to check that you're doing it right. Plus 474.5 is 579. All right. So now we finally got our expecteds. Let's circle them. And now we are ready to just, all we have to do is plug them into this formula. Okay? Any questions so far? Oh, all right. Now, what did I say here? Before we just plug, because the rest is just plugging it into the formula. Just plugging it in. For example, we're going to take each cell, So our first cell will be what? Our observed. 17 is our observed, minus the expected, 3.9, 17 minus 3.9 over 3.9. I've got to square that numerator. And then I have to do it for the other 5 cells and add them up. So it's a lot of work. So before we get into that calculation, before we get bogged down there, I just want to show you the shortcut that might help you, especially on the exam. Because you might somehow get into exam mode. Now that you understand this reasoning, there is a sort of, some people prefer this shortcut method of figuring out all these expecteds, okay? So the above reasoning for finding these expecteds is the same thing as using this shortcut. What is the shortcut? For each cell, multiply its row total times its column total and divide by the, whoa, something weird happened and that was my hand and I did something different. Oh, which one is it? Oh, rotate, I bet. No. Yeah, there we go. Okay, so for each cell, we'll do that. We'll follow this, all right? So what does that mean? So you take a cell right here. There's 6 cells. I don't care which one you take. Let's just take that cell. All right. What is its row total? Total. It's 47. So that's 47. That's the row total. So you just look there. Then multiply it by its column total. That's its column total. So you multiply it by 52 and then divide by the overall total by everybody in the population. This is the overall total. So we'll divide it by 626. Do you see why that works? If you have a calculator, and I don't have mine, but 47 out of 626, 47 out of 626 is 7.5%. It's actually the decimal. It's 47 over 626 is exactly 0.075. So that's why it works. All right? So you're really doing exactly the same thing. All right, and if you miss these, and if you put it doesn't really matter if you put the 52, if you just multiply these two in any order by the overall total. So let's just take a random one like right here, so you just get practice with it. What are you going to do? What are you going to do? You're going to go to where? It doesn't matter which one you go to first. If you want to go to the row total first, you can. So you go to 579, then the column total, see? Here's your row total, column total, times 61, and then you divide always in the denominator for every one of them will be 626. Okay? So why don't you, if you want to get used to doing it that way, that's easy too. A lot of people prefer that. Okay? In every one of them, it's going to be 626. You could just fill that in. Every one of them. That's your overall total. And then all you have to do is, whichever cell you're in, this one, just go multiply those two numbers together. Okay? 47 times 61. And if you get your rows and columns, say 61 times 47, it doesn't matter. So you can do it that way too. Questions so far? Now, you're probably all wondering, how am I going to remember all this on the final? This is just coming up in a few days and I have a zillion other things to do. Basically, I am not going to make you do a zillion calculations because it's Scantron and I can't go through and check your work and see your careless errors. So basically, I'd probably just say, okay, figure out the expected for one cell. So you'd go to one cell. Let's say it was this one. You could get the overall total and then just multiply the two totals here. Okay? You're not going to have to. On your homework, you are going to go through the whole problem because you have time. And it will really help you because I want you to learn it. But face it, these Scantron exams are not the best way to test. And I can't make you do a zillion calculations and check your work and grade you fairly. So I'm just going to have to break it up into little pieces. And you'll see because you'll have some practice tests to practice on. All right. So that said, we are finally able to do the calculation. And we're just going to have to use, this is it. So all we have to do, if you can spread your sheet out like this and go on to the next page, here I can't see both, but you can, because we are going to be computing it right here. I wish if I zoom out a little bit, but no. But what are we going to do? Okay, so it's the sum of the observed. So why don't we just, we're going to have 1, 2, 3, 4, 5, 6. Look, let's make this a bold line here. We only have 6 cells that we're talking about. 6 observed, okay? We only have 6 cells. Those are observed. Now let's do the same thing here so you don't get confused. We're only talking about these 6 cells right here. These are headers, and I should have bolded them. All right, so we have these 6 numbers here, and these 6 numbers here are our expected. These are our expected. These are our observed, all right? And for each cell, we're going to take our observed minus our expected, this, observed minus expected squared, and divide it by the expected. Then we'll move on to the next one. Do you see what I'm doing? 8 minus 44.6, square it over the expected. Then we'll move on to the next one. 22 over 38.5, square it over its expected. Then we'll go to the second column. So this is all I'm doing. Do you follow me? Not if you follow me, because I don't want to lose you with all this boring stuff. Question, yeah.
What's the expected that you're dividing by?
It's the same number. Let's do the first one. It's this. So for example, the first one, should we do the first one? Let's do the first one. So we have, the first one is, now I got to look back. Oh, okay. The first one is, what's our observed? You tell me. At the first cell, what's our observed? 17. Everybody agree. What's our expected? 3.9. What do I have to do here? Square it first. Now, I'm going to divide by expected. So what is our expected? That is our first cell. Okay? Do everybody see that? Now let's go to our next one. We have to do, let's do the top row and then the next row. And we're going to add them all up. So the next one, okay, what is our observed? Hello? 8. Minus our expected. 4.6. Square it. Divide by what? Our expected. Go to the next one. All right. What is our observed? 22. Does everybody see that? 22. Minus our expected. Ooh, I can't even read that. 38.5. Square it over the expected. That's our first row. Done. Now we have to do our second row. Okay, our second row, we're adding. We're adding all 6 together. I'm just lining them up in rows. You can do it any way you want. It's just easier for me to keep it straight. Now I'm on my second row. Okay, so now on my second row, what's my expected? It's just 35. Does everybody see that? No, that's my observed. Does everybody see that? 35. I'm right there. Minus, I'm going to minus that, 48, okay? Minus the expected, 48. Oh, that's 4.8? Oh, it's 48.1. Thank you. Boy, it's so easy to make a mistake here. And you know what? I'm going to have to allow more tolerance on your homework. Because I think there's some, I don't want you to have to struggle so much. I'm going to have to put a little more tolerance in if I gave you 99 tries on one of them. But I don't want you to waste your time just trying and trying. I should just put more tolerance in. Okay, over, what do I do now? Let's not lose our train of thought. What is this? Is it the expected? Is that right? Okay, now I move on to the next one. We have 53 minus our expected, which is 56.4 squared. These are our differences over the expected. And then finally, the last one is 491 minus 474.5 squared over 474.5. Whoa, lots of work. Again, on the final, and even on your, I'm only going to probably give you some of them, and then you'll just have to fill in like maybe 2 of them or something to get the chi-square. Okay? So now we do all that, and you can do it all out, and some interesting things develop. Like this turns out to be 13.1, and this turns out to be negative 13.1. You should look for patterns like that. And this will turn out to be 3.4, and this is negative 3.4. They sum to 0. We'll talk about that later, but you can discover those patterns on your own. Let's just add these up, and we get 58 as our chi-square statistic. Okay? Trust me, that's what we get. All right. Whew. Take a breather. Drink of water. All right. Now, 50, we have to look. This is our statistics. It's not like a z where we'll know right away by looking at that normal curve. We have to figure out the degrees of freedom. The degrees of freedom. So how do we figure out? Well, the degrees of freedom for a chi-square test is the number of rows minus 1 times the number of columns minus 1. Why? What is that even saying? The degrees of freedom is equal to, let's think about it, the number of rows minus 1 times the number of columns minus 1. It's really the number of categories minus 1 for one variable times the number of categories minus 1 for the other. That's really what it is. It's exactly, and first of all, let's figure it out for this case. Rows, see how many, there's 2 categories here. There's 2 categories in this variable, which is, I guess we call these rows. Don't worry which one you call rows or which one you call columns. It doesn't really matter. They're interchangeable. So we have 2 categories for this one. And how many categories do we have for our other variable, for tattoo status? 3. So this is the 3 categories. So that's, if I say the number of rows, the number of columns, which everybody says, people get confused sometimes because they start adding in the totals. No, it's really your number of categories in here minus 1 times your number of categories here minus 1. So let's do that first. So it's 2 minus 1 times 3 minus 1, which is only what? 1 times 2. Okay, so this is the same as, just to not get confused, the number of categories minus 1 for one variable, doesn't matter which one, for the row or the column variable, times the number of categories minus 1 for the other variable. That's all we're doing here. Remember, when we had just one sample, it was for a chi-square test, it was the number of categories minus 1. Because if I gave you 5 like if they had 6 categories and I gave you 5 of them, the 6th one was determined. Now watch what happens. When I give you, let's just look at any of these, I don't care which one. When I give you just 2 of these, it has 2 degrees of freedom. Because if I give you like these 2, you can figure out the other ones are determined. These 2, let's say, or any 2, like these 2, but let's just start with these 2. If I gave you these 2, you'd know this one had to be 38.5 because they have to, you'd say 3.4 plus 4.6 plus what adds to 47? It has to add to 47. So there's only one thing that makes it add to 47. Same, so you get that one. Now, it had 3.4 plus what adds to 52? These 2 have to add to 52. So that's the only number that adds to 52, 48.1. Same with all of these. So really just 2 of these will determine all of them. The number of categories minus 1 times the number of categories minus 1 here. All right, we still have not solved this problem. Finally, find P. So what do we have to do to find P? You know what I have to do. Tell me what to do. Do you know what to do here? What should I do? Where should I go? Go to chi-square table and check what? Check 2 degrees of freedom. All right? Row. Let's do it. So we go to, and this will be on your exam, on your final, and so you'll go to the last page of your final. It'll look like this. And if this was the problem, the only thing you need to look at is this second row here, because that's 2 degrees of freedom, okay? 2 degrees of freedom. And we want to see how far out it is here. And remember, we reject the null at 5% or less. So we only need a chi-square of 5.99, and we could reject the null. We are so far out. 5.9 is probably right here. Where are we? What is it, 58? We are off the page. Off the page. So what are we going to say? We're going to say that, what can we say? The chi-square equals 58 is tiny, tiny, tiny. Is a tiny p. Almost, it's never quite 0, but it's about as close to 0. It's almost 0. That would be the answer. It's a tiny p, almost 0. It's way off the charts. The chance that if there was no difference between these groups, if finding out whether somebody has a tattoo or not tells you nothing about whether they have hepatitis C. You have no idea. It tells you nothing. It's not at all, they're completely independent. If that was true, we'd see a result like this almost, I don't know, almost never. So obviously, the 2 are associated. This is extraordinary evidence, no doubt in my mind, that the 2 are associated. That the 2 go together, okay? It's obvious here. Okay, so we have overwhelming, so we reject the null, that they're independent. We reject the null, and we have overwhelming beyond belief evidence. We'd convict for sure in a court of law, overwhelming evidence that whether or not somebody has hep C does depend on their tattoo status, okay? That overwhelming evidence that hepatitis C is dependent on tattoo status. That doesn't, okay, so what does that mean? So we all agree that they're not independent. You know, if I told you somebody has tattoos from, we could look at the data from, let's say, which one was more likely? We should look at it. Which one was more likely here? From a parlor than from somewhere else? Okay, so this one was the most likely. So if you find out that somebody has tattoos from a parlor, probably because when, you know, from somewhere else they're not sharing needles, right? So from a parlor and you find that out, there's a much greater chance that person has hepatitis C than if they had it, you know, a tattoo done from maybe themselves or no tattoo. All right. Now, though, the question is, this goes back to correlation and causation. So let's talk about this. Way back to, you know, we've talked about this a lot. So now can you conclude from this study that tattoos, getting a tattoo causes hepatitis C? Do we know that? Why? Why? Why can't I say it's the hepatitis? Why can't I say it must be the dirty needles that's causing it? What? Correlation is not causation. Okay, correlation is not causation. The two are associated. So why are they associated if it doesn't cause it? What else could be going on here? What? People who get tattoos might be more likely to get a hepatitis C. Why? Yeah? A confounder. Yeah. What would be the let's think about it. So let's just go back, because this would be, you know, relates back to what we were talking about before. Okay, so the question now is, as you said, you know, all we know is that it's correlated, okay? But that doesn't mean, so we know Hep C and tattoos are correlated. I'm not spelling this right. But that doesn't mean causal, are correlated. Okay, so now the question is, I sort of want to know, does getting a tattoo, do tattoos, and I keep spelling it wrong, it doesn't have two T's, do tattoos cause Hep C? Maybe. Or, as you said, is there a confounder that's really causing the Hep C, but is somehow linked to tattoos, making it look like they're the culprit when they are innocent? Really? All right. So, first of all, if there was a causal link, it would be dirty needles, right? Doesn't everybody agree? So that could happen, maybe. And it could be both. It could be dirty needles, and it could be also a confounder too. What would fit in here? Risky sexual behavior does cause Hep C. Risky sexual behavior. What do you mean? Sort of, how does it cause it? Yeah, I guess we don't have to go into the details, but probably, yeah, risky sexual behavior. Does that cause? That does. Actually, my girlfriend got it that way. So yeah, it does cause Hep C. How does that relate to tattoos? Yeah, people who have a lot of risky sex might be more likely to, you know, want to show off their body with a lot of tattoos. Does that sound reasonable? No? I mean, I'm not saying everybody who has tattoos has risky sex, but if you look at, the retirement home where my mom is, there's nobody with tattoos all over their body. Not many of them are, whereas if you went to, you know, I mean, I think there's probably some correlation.
It could just be risky behavior in general.
Risky behavior in general, like with drugs. Risky behavior, drugs, sex, and people who do that might also have more likely to have risky behavior, just get tattoos. They're just more risky types. That's good. That's a good point. Okay, so risk takers. How about that? Risk takers, especially drug and sex risk takers, because they're drug and sex risk takers, certainly are going to be more likely to get hepatitis C and probably are going to have tattoos. So that would be a likely confounder. And the only way we could tease that out is to separate them into groups. Okay, very good. Excellent. Questions so far? So we know the two are associated, but we don't know if it's a causal relationship. All right, now we have what, a few minutes, about 15, 20 minutes left. Has anybody looked at the homework so far? Yeah? How's it going? How's it going? I want to take a look at it because some people were saying there were problems with it. Has anybody discovered problems with it? Let's just take a look at it and see how it's going. Okay, remember this problem? In bonus survey 4, students were randomly assigned to take 3 different versions of the survey. Everyone's questions were worded the same. The only difference was which picture accompanied your questions. The questions. These were on abortion. Which comes closest to your view of abortion, and what basically I thought if it was accompanied by this picture versus this picture versus that picture, that maybe people's feelings on abortion would change. They might give different responses. Do you think they would or not? Do you think we're going to find a significant difference or not? We're going to have to do a chi-square test, just intuition. Do you think the people who received this, my idea was that people would be more pro-abortion if the less they thought of it as a real baby. Okay, so I figured these people would be the most pro-abortion. These are both real babies, but somehow I thought maybe this one was a little cuter. Anyway, I thought there might be a difference. So, do you want to vote on it? I'm going to start it. If you think that there's really not going to be any difference, the null is going to be true. That, your feelings about abortion are not going to be influenced by pictures like that, vote A. You can't get this wrong. If you think your feelings of an abortion might have been slightly shifted, you might have been given different answers depending on which picture accompanied your survey, then vote B. You can't get this wrong. This is just to make it more interesting when you do the test. What's your intuition? Do you think it came out significant or not? Okay, so if you think these pictures make no difference in your answers, write A. If you think they influence people, write B. So let's see what you think. All right. Well, stop it. No, what? You didn't want it to be stopped? Okay, well, you can talk to somebody. Talk to David afterwards. He'll help you out there. Okay. How many people didn't get it? Just one person? Okay, we'll just talk. Okay. So most of you think it's not going to make any difference, but it's close. It's 53 to 46. Interesting. And what's C? Was that you? Okay, now. All right, so how would you go about doing this? So this is going to be one of your homework problems. And what I did was because, you can read all about it, but basically I just did 2 categories. Either you thought it should be legal or illegal. You can read how I did that. And whether you have picture 1, picture 2, picture 3, and only 573 people did this survey because unfortunately we didn't keep it up long enough. Our next survey you're going to have up for a long time and everybody will have a chance to do it. All right, so this is how it came out, and those are observed. Now what are you going to have to do? You're expected here. How are we going to do this first one? Should we just try? How would we do this first one? We'd take what? 344 times 211 divided by 573? Okay, tell me what that is. Somebody has a calculator so I can see if that's right. For the expected. What? When's the last homework due? It's due Wednesday. But I'll put it up right away and it's real short. This is the second to last homework. Do you want to do this problem to see if it's right? Right here? No. Okay. I don't have a calculator, so I can't unless somebody gives me the answer. 126.7. I'm just going to do this one part. I just want to see if it's working. 126 point what? 0.6. 67. Let's just make sure you understand how to do this. So you're going to take that. Did you take that times that and divide it by that? Is that what you did? 211 times. Okay, let's see if it works. Yahoo! It does. Okay, so then after you get all these, you're going to have to do your observed minus your expected squared over the expected and get those 6 answers. And then you'll finally see whether it's significant or not. Kind of interesting. Okay, so that's your homework. Any questions on that? Now you all think you're ready to go. Look at you, but you're not. You are not. I just hate to disappoint you. You just all have this little eager bunny look about you. No, I'm sorry. That was just taking a quick break, and we just have one quick problem to do that I think will cement this in your mind because it's a very intuitive problem. And we're going to boil down this chi-square, let me show you, into a very intuitive problem. Okay? How many clicker questions did we have? Just one? Oh, come on, you just have to say whether you're here or not. Just say, A, you're here. Because I want to give everybody who's here an attendance point. A, you're here, B, you're not, and you don't want a clicker point. A, you're here, B, you don't want a clicker point, and C, you're willing to accept a C in the course. If I have to give out, you'd be happy with a C. D, you're willing to accept a D in the course. E, you're willing to accept a, let's just do that instead. A, you would like an A. B, you would like a B. C, if you had your druthers. That's what you're going to vote on. No wrong answers. I just want to see how you decide. A, it's not going to necessarily work that way, but A, you'd like an A. B, you'd like a B. All right, let's see what happens. Everybody vote? All right. Let's stop this and see how many people said A's. All right, we did have 2 people who said they'd accept an F, 1 with a D, 4 with a B, and the rest A's. Okay. Interesting. There's always something. Okay, now back to the document camera. Okay, now I said this one's going to be easy. So why? It'll be easy if you focus. Let's focus. I know it's hard. Take a deep breath. Focus. This is actually important because it shows that you can do the same problem as a 2-sample Z and as a chi-square. We already did this problem in chapter 1 as a 2-sample Z. You can look back at it. Do men fall in love at first sight more than women? Another alternative is to do it as a chi-square test for independence. Does falling in love at first sight depends on whether or not you're a male or a female? Okay. Remember this, 500 men and 500 women were asked, have you ever fallen in love at first sight? We looked at this difference, this 8% difference. We saw it was significant. P was 0.05. Now, the null is falling in love at first sight is independent of sex, of whether you're male or female. And this says, no, it depends. So how do we do this? Our alternative, by the way, does not specify a direction like it did in the last case. So what do? The first thing we have to do is we have to change the percents to counts. And that's the hardest part about it. Okay, so 44% of the 500, that's 220. That means this is 280, because it has to add up to 500. 36% of 500 is 180. I'm just changing them. That means this is 320. And that means this adds up to 400, and this adds up to 600. So now we have our observed counts. Shh, okay. Now we have our observed counts. We have to get our expected counts, and this time it's easy. Why? Because the null says, as you recall, that male and female are no different on this question. And the reason it's easy is because there's a 50-50 split between males and females, 50-50. And we had 400 people who said yes, and 600 people who said no. So if we're saying that there's no difference between males and females, then the ones who said yes, 400, if our sample is 50% men and 50% women, then among the 400 people, how should this be split? 50-50. So what should I put here? 200 and 200. And if you didn't see that and wanted to take for example, for this one, if you didn't see that and wanted to get that and took your what? 500 times 400 over 1,000, you get 200. So you could do it that way too. All right? But intuitively, since there's a 50-50 split here, how do you think this should be split? Hello? 300 and 300. And now we have our expected. So this was very easy to get. And all we have to do is do what? Our chi-squared is going to be what? We're going to take our observed, 220, minus, you tell me, the expected, square it, and what do I divide it by? 200. Let's move to the next one. Plus 280 minus its expected, 300, squared, divided by what? 300. Now I'm adding all four of them. I'm going down here. 180 minus its expected squared over 200. And our final one, whoops, just don't get confused here, 320 minus what? 300. Oops, sorry, you can't see that. 320 minus, now you can't see that. Thank you. 300 divided by what? 300. And we just add all those up, and these add up easily, because that is what? 20 squared over 200, and that is negative 20 squared over 200. I'm just going to add them all in a row. And this is negative 20 squared over 200, and I made a mistake right there. And this one is what? 20 squared over 300. So what do we get? This is 400 over 200. This is illegible, but what it says is 400 over 300, so that's 1 1/3. This is 400 over 200, which is 2, and this is 400 over 300, which is 1 1/3. So we get 6 2/3 is our answer. Whoa. Is that legible to everybody? Hello, is it legible? Yes. All right, now we've got chi-squared. equals 6.67 degrees of freedom. Can you figure it out? What's it going to be? How'd you figure that out? 2 categories here, minus 1. Good, you figured that out fast. And here you have 2 categories there, minus 1. So you're absolutely right, it's 1. It's only 1 degree of freedom. And when we look that up, let's see if it's significant. It was when we did it the other way. And it is 1 degree of freedom. It's P equals 1%. So we get P equals 1%. Before we got P equals 0.5% because we did our alternative was just that men were more romantic, whatever, that they were likely to do this, and so we had a one-tailed test. Don't worry about that too much. We reject the null. See you next time. Have a good weekend.